Hello AP Stats students. In this video we're going to talk about random variables and probability distributions. Now you do not have these notes in your note packet that I gave you before, I think I've posted those on your Canvas page, so if you want to pull these up so you have a copy of them to look at, you can. But I'll also make sure that you get a copy of these in the future. Alright, so with random variables, what we mean is it's a variable that takes on a value randomly. So there's some kind of reason it just takes a value. Okay, maybe it's genetics, maybe it's who knows what. But examples of random variables are things like rolling a dice, and the number that we get on the dice roll, that would be a random variable. Number of heads when we toss 5 coins, we could get 0, 1, 2, 3, 4, or 5. The number of children in a family, number of people in a store at a certain point in time, number of light bulbs in a box that don't work, person's shoe size. Those are all examples of random variables, and those are actually discrete random variables, which is what we're going to really focus on today. We can also have continuous random variables. Remember, the difference between discrete and continuous is discrete can only take on certain values, whereas continuous can take on any value. Now, it may be within a range of values, but it can take on any value within that range: halves, quarters, wholes, whatever. So examples of some continuous random values would be like the height of a tomato plant, or the weight of a chicken egg, the time between eruptions of Old Faithful, the length of cat whiskers. Okay, all of those things could take on as many decimals as we could measure to if we wanted to. So that's why those are continuous, where the ones up above are discrete. What we are looking at, though, is a way to kind of organize the probability of these outcomes. And so we create these things called a probability distribution. And a probability distribution is a list of all the outcomes that the random variable can take. So like if we were rolling a dice, 1, 2, 3, 4, 5, 6. And then the probability of each outcome happening. Now with a dice roll, it would be the same. It would be 1/6 for each one of those. However, with a lot of things, the probability is different depending on which outcome we're looking at. But those outcomes have to be disjoint or mutually exclusive. In other words, there can't be an overlap. When we have an outcome, we've got to know which slot it fits into on our probability distribution. The probabilities all have to be numbers between 0 and 1. Okay, that's a definition of probability in the first place, but it's got to be true on our probability distribution as well. And then the sum of all the probabilities have to equal 1. In other words, we can't leave out any outcomes. All the outcomes have to be there. If we're rolling a dice, we can't put 1, 2, 3, 4, 5 and leave out the 6. Okay, all of the outcomes have to be there. And we can't use outcomes like even, prime, those sorts of things, because there's overlap between them. So a probability distribution has to have a list of all the outcomes, all the probabilities have to be between 0 and 1, and the sum of probabilities have to equal 1. So let's make a quick probability distribution here for rolling 2 dice. And so here are all the different possibilities that can happen when we roll 2 dice. Okay, so when we look at this, we've got the black dice is 1, and the white die is a 1. And so the sum in that particular spot would be 2. Now that's the only place on this table where we get a sum of 2. And so since there are 36 outcomes in this table, the probability of getting a 2 in our probability distribution would be 1 out of 36. Now we can write that as a fraction. We could also write it as a decimal. So if we took 1 divided by 36, then we could write down the decimal point 0.02. Let's round and make it 0.28. Okay, so go ahead and fill out the rest of this probability distribution. Pause the video and do that. Okay, so for 3's, we should have found these two give us 3's, and so we get 2 out of 36, or 1 out of 18 if you want to write 1 out of 18 instead. Or if we want to write the decimal, we can do that. I'm going to save us a little bit of time here. I'm not going to write the decimals. Okay, 4's, there's our values that give us 4, are these 3 right here. So it'd be 3 out of 36, or 1 out of 12. Okay, when we start looking at 5's, we've got 1 and 4, 3 and 2, 2 and 3, 1 and 4 again, just the other way around. And so we get 4 out of 36, or 1 out of 9. Okay, for 6's, there's this box, this box, this box, this box, and this box. And so there's 5 out of 36. Okay, that doesn't reduce. Okay, for 7's, you should have counted 6 different outcomes that would give you a 7. So notice these all kind of lie along diagonals. That kind of helps a little bit. Okay, for 8's, we end up with 5 out of 36 for 8's. For 9, we get 1 out of 9. There's 4 of them, 4 out of 36. For 10's, there's 3 out of 36, or 1 out of 12. For 11's, there's 2 out of 36, or 1 out of 18. And for 12's, we get 1 chance out of 36, of getting that. So that would be our probability distribution. Now, are all of these outcomes disjoint? Is there any confusion about where one of these outcomes would fit? Okay, if I pick any one of these combinations, I know exactly where it ends up in my probability distribution. So these are disjoint. It would not be disjoint if I used like two numbers greater than 5, 7, evens, that kind of stuff, where I mixed it all sort of together, because I wouldn't know where am I going to put the 8. Am I going to put it in even numbers, and I'm going to put it where numbers greater than 7? Where's it going to go? And so that's what we mean by disjoint. So yes, all of these are disjoint. Okay, are all the probabilities between 0 and 1? Well, none of them are bigger than 36 out of 36, and they're all at least 0 out of 36. So yes. And it's okay to have 0. We just can't have, and it's okay to have 36 out of 36. We just can't have anything beyond that. And does the sum of the probabilities equal 1? Well, we could add these up. If you add up 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1, we get 36 out of 36. And so the answer there is yes, the sum of the probabilities do equal 1. So all of the three things that are required to make it a probability distribution are there. So this would be a probability distribution. Okay, go ahead, and we want to look now at probabilities off of these probability distributions. And so based on the random variable we've talked about, okay, rolling dice and coming up with the sum, if you see this notation, what do you think that's going to indicate? Well, that's going to indicate the probability of getting a value less than 5. So the probability of the roll is less than, not less than or equal to, but just less than 5. So if we look at our probability distribution, what's the probability of getting a roll less than 5? Well, in our chart here, the rolls that are less than 5 would be this one, and this one. So we would want to add that up. 1 over 36 plus 2 over 36 plus 1 over 12. These are mutually exclusive outcomes. Okay, that's the whole disjoint part here. So since they're mutually exclusive, I can just add them together. And so if I take 1 out of 36 plus 2 out of 36 plus 3 out of 36, that gives me 6 out of 36, which would, of course, simplify to 1 out of 6. But didn't want that one. So 6 out of 36, which would equal 1 out of 6. Okay, what's the probability that we're looking at here? Go ahead and figure that out. Okay, so if we go back to our table, we want probabilities that are greater than or equal to 6, less than or equal to 9. So let's highlight here which probabilities we're talking about. Okay, 6 is included because it says greater than or equal to 6. So is 7. So is 8. There we go. So is 9. And so if we add these up, we got 5 out of 36 plus 1 out of 6 plus 5 out of 36 plus 1 out of 4. And so let's see here, we get 20 out of 36 when we do that. And so, because there are 20 outcomes that are represented between that area of our distribution, and of course 20 out of 36, let's see, that would reduce to 5 out of 9. So we can make a probability distribution then for any set of probabilities that we've looked at. We just have to write down the probabilities for every single outcome. So here's another example. Go ahead and create a probability distribution for this and then check to see if it is a probability distribution. Pause the video if you need to here. Okay, so we need to make a list of our possible outcomes. So what are the possible outcomes for this discrete variable number of VIPs? Well, they can bring 0, they can bring 1, or they can bring 2. Those were our only choices. So we just want to list those probabilities. So it says 10% have not brought a VIP. So that would be 0.1 or 0.10. 60% have brought 1. So that would be 0.6. Okay, it doesn't tell us how many brought 2, but we can figure it out because we know if this is a probability distribution, this has to equal 1. And so this would have to equal 0.3. And so all of our probabilities are between 0 and 1. They add up to be 1. And these are disjoint. Okay, we don't have a situation of trying to decide which value it would go into. Okay, when a student shows up with a VIPs, we either know, are they 0, are they 1, are they 2? We don't have to think about which slot they fall into. Okay, so that would be a probability distribution. Easy enough. Okay, we can take these probability distributions and we don't always have to have them as a table. We can have them as a graph like we do here. And when we look at these graphs, we can describe them using the same terminology we use to describe distributions way back at the beginning of the year. Remember the SOX acronym, shape, outliers, center, and spread. Now with probability distributions, we don't usually have outliers, so we don't usually worry about that, but we do talk about the shape, the center, and the spread. And so if we looked at this particular probability distribution, this is the one for rolling the dice, notice that the shape is symmetric. Okay, where would you say the center is? Well, it's right here, and so it's got a center is 7, and what would the spread be? Well, the spread goes between 2 and 12. However, we might say even that most of the data is between 5 and 9. So I might say, I should have put that down first. All values are between 2 and 12. Most are between 5 and 9. And so that's going to be the spread. Now, just like we talked about center with the mean and spread with standard deviation, in our next video, we're going to look at what the mean and the standard deviation would be for one of these probability distributions. Now, we can also give probability distributions as what we call cumulative probability distributions. And basically, a cumulative probability distribution is kind of like a cumulative frequency distribution, like we talked about at the beginning of the year. And so remember, a cumulative distribution just accumulates the probability up to that point. So on this is the same distribution we're looking at. It's the outcome of 2 rolled dice. When we look at 9, though, in this distribution, what it's telling us is it's telling us the probability of getting a number less than or equal to 9. And so when we look on here, and that looks like it's about maybe 0.81, that 0.81 would be the probability of getting a value that is less than or equal to 9. And so whatever number we see on this chart, that is corresponding to the probability of getting less than or equal to that number. So the probability of getting less than or equal to 3, not very high. Probability of getting less than or equal to 8, a lot higher, over 50%. In fact, once you get past 6, as soon as we get to 7, the probability is greater than or equal to 50% that we're going to get a number bigger than 7. Okay, so that's what a cumulative probability distribution is going to be. It's just the cumulative value, or the value that's less than or equal to that number. All right, so that's our quick little introduction into probability distributions. We're going to spend a little more time talking about those in the next couple of videos, but today basically you're just going to be making a probability distribution and interpreting some probabilities off of a probability distribution.